You might have to touch with the mouse or first one. Yeah, there you go.
Okay, so just a quick outline of what we'll be doing this afternoon. So first, I'll just speak a little bit very fast about overview of spacing regression and why we take these things into consideration and why do they matter. Then we'll talk about data and non-spatial regression. So just again, I mean, we have very short time today, so everything will be a brief overview. We won't go into much details, but I'm happy to, if you want me to speak further about any of the issues that I start talking here, just let us know. Julia is taking care of the chat for you that are following remotely. So if there is anything, just let me know and I can dive deeper in whatever you want. Then we'll go speak about spatial regimes, spatial weights, and then finally spatial dependence models. So then we finally begin with the spatial regression. So everything first is more like a brief introduction or just a review. Okay, spatial data. So, I mean, if we talk about, for example, retail markets or anything like that, we have the most important aspects of a retail property or something like that. They are location, location, and location, right? So location is something that is real important, not only, of course, for retail market, but to understand economic interactions or socio-economic interactions or how people behave. And we have contagion, we have spillovers. I mean, all these things, they do happen somewhere. And this space tag may really bring more information about the event that we might be studying. So it does, most of the time, it does really matter where something is happening, the interactions, the social between people, firms, or whatever. It really depends on where these things are happening to see how exactly they will, what the results will be. So if you have, for example, two people who are interacting like in a given place, you will have all their cultural backgrounds, you'll have the institutions, you have regulations. Everything may be different if you had the same two persons doing whatever in a different location, right? So location may really play an important role in shaping the relationships that we have between people, firms, or businesses, or whatever you think about. So what we'll be talking today is that whenever we're dealing with this kind of information or data that is actually ordered in space, and of course, it's also happening at some point in time, so we may even have this additional dimension going on as well, but not today. So today we'll focus on space. So whenever we have that data is ordered, or at least has some spatial information about it, spatial correlation will not be an exception. It's usually the norm. So what we have is that near things are more related to each other than things that are farther away. So since we have this relationship going on, if we are dealing with these social interactions or these spillovers or contagion or whatever type of spatial interaction that we think of, we need to take this into account because it will not be just, another layer of information. It's usually something that is shaping the information that we see. And an interesting thing about space is that not only space may shape the kind of interactions that we have in the sense that I've already told you about, like the institutions or regulations or whatever. Space is also produced by our interactions, right? So the space that we live, the neighborhoods, the cities, they are a result of the interactions that we have. So there is this strong simultaneity going on there, that people shape space and space will shape their relationships. So this is something that we need to take into account when we are analyzing this data, because it may really have an important influence on the outcomes that we see of any relationships between two different variables that we look. So when we take all this into account, then the fact that space not only affects the relationships that we have, but is also affected by them, we can easily think that there isn't, space is not really something that we can think like as a structurally stable. So there is some structural instability over space in the sense that the way space influences our relationships may change over time because our culture changes over time. our regulations change over time, the institutions change over time. And since we are always shaping the neighborhoods and the space where we are over time, of course, the influence of space will change as well. So, I mean, the dynamics here are really important to take into account. So we need to be able to measure how these things work and how it affects what we're studying. So there are many different types of spatial data. Today, what we'll see is point or event data for the examples that we'll have. But of course, you can have different types. You can have, for point data, you can have crime occurrence, you can have health facility locations. We'll see the example that we'll use from Dani's book is Airbnb locations. So this type of data is usually the best to work for spatial analysis because you have the precise location of an event or individual or whatever. And with that precise location, you can do anything you want. So you avoid some issues that usually we have with different type of data that come from aggregation or zoning or whatever. I'll speak a bit more about this. So this is the type of data we will work with today. It could be continuous spatial data. So for example, usually we have data on pollution, on air quality, on land use, on soil that is more continuous over space. And these will require different types of methods to be dealt with. So, I mean, it is something we can have. And usually for a regression, what we usually do when we have continuous space is that we make it discrete. So we do some zoning at it. We create either squares or hexagons. And then there's a whole discussion about like what hexagons, what are the issues with hexagons or squares or whatever. So, I mean, we can create a regular grid on top of continuous data and use the methods that will be seen today as well. Or what we can have is a discrete spatial object. So we can have, for example, census tracts or counties or municipalities or states or whatever that shows us some data. And usually we'll have data on income, GDP, any other kind of aggregate data. It will come in this format. And then, of course, the heterogeneity that we have within this discrete spatial area is important to be taken into account. It may result in some issues, but anyway, so this is another common type of spatial data that the methods that we'll see today are able to handle. So whenever we talk about this, so analyzing spatial data and what does this all mean? So the spatial data science, or in this case, just more the analysis, the whole idea, if we want to make it very simple, is that we have geospatial data whenever we have a value or an attribute of a given individual, a given point or whatever, and we have its location, right? So the data has both things, the attributes and a location tag to it. The analysis will be called like non-spatial analysis only when we are evaluating these features and the location does not matter, in the sense that the probability that we would see that data, for example, the probability that we would see an observation with a high wage, it would be the same regardless of the area. So think about a city. I mean, if you want to draw a sample and you want to draw someone from a sample, a person that has a very high wage, would the probability of drawing that person from a sample be the same in every census tract that you have in a city? Usually not, right? So this is the thing that we have about the spatial data. If it's non-spatial data, the probabilities should be pretty much the same of drawing a given information or an observation from anywhere in the map. So there would be a locational invariance. But in spatial analysis, it's not like that. When we do spatial analysis, if the location changes, the information content that we have of this data may change as well. So the probabilities of being able to draw a given observation, it depends on where it's being drawn from. So this is what differs spatial analysis from non-spatial analysis. Okay, so a quick refreshment on regression, and then we'll begin. So when we're talking about non-spatial regression or classic models or
Pedro.
ordinary least squares, OLS, what we're trying to do is to relate a given variable of interest, in this case, a y variable, right? So our dependent variable, what we want to try to explain, or at least try to understand how it correlates to different attributes. And then we have this X matrix, which will contain the attributes that we want to see how they related to our y vector, right? So to our important variable, the variable that we want to understand about. So the X will be the variables that we will try to see how well they correlate with Y and how well they can explain Y to us. The beta vector will be the coefficients to measure this relationship, to show how Y varies according to the changes that you have in X. And then we have an error vector that will make sure that this equation matches, right? That the Y, all the differences that you have from the expected values given your X matrix and your observed Y vector, that you actually get a fit in this model. So we have this error model to ensure that. In this classic model, in this OLS, there are some important hypotheses for it to actually work, right? For us to be able to draw this a small line that takes care of the average of the data and gets this equation solved. Some of these hypotheses are that this error term or its estimated values, the residuals, it must have a constant variance. So this is an important hypothesis in the sense that the variance must not change across observations. And if I'm saying across observations, it must not change in space as well, right? So think about it again. If we're trying to explain wages, and here we have maybe education, age, and whatever other individual aspects that are important, the variance of these residuals or the variance that we have from the difference that we have in the line that deals with age and education and wage should be the same across space. And of course, it usually is not, right? So this is a hypothesis that is usually not met in spatial data. So this is something that may be an issue. And in addition to this, the residuals should not be correlated to each other. So again, I mean, if you think about a city and depending on the distribution that you have for your X matrix there, what you're saying is that the part that you cannot explain on wages, it shouldn't be spatially, there shouldn't be any spatial concentration on that. So you shouldn't have any space in your city that has like the most higher wages, even though the education levels or the ages are not as homogeneous or as high in there. See, so again, it's a kind of an unrealistic way to see some applied or some applications of this data. If we're dealing with the spatial analysis, usually these hypotheses, they just don't meet, we're just not able to meet them. And whenever we're thinking about spatial data, and I'm giving you here examples about like within a city or census tracts or things like that, it's really important to consider what we are actually studying. So what is the spatial process of what we are seeing and what we actually observe as data. For example, if I'm studying, let's say dengue fever, so I have like the mosquito, how far it travels, so how I can have contagions for dengue fever within a city. But if I don't have data on actual blocks or buildings, and my data is aggregated, for example, at the county level, does it really make sense to think about this contagion going on across counties? Like, is the mosquito location that homogeneous? Can it fly that far? Basically, that's it. And it cannot, right? The mosquito has a very limited range of fly, so it won't be able to do all these things. You'll be measuring pretty much just the mosquitoes that are all across the borders of the localities you are checking to see if that interacts between counties. So the spatial scale of what we're studying, like what is the scale of the process that we're studying? And what is the scale of the data that we actually have also, or the scale of how we observe the process that we're studying? These things must match, otherwise we will have issues. Usually these issues may also result in ecological fallacy. So for spatial data analysis, we have a very special type of ecological fallacy, which is the modifiable area unit problem. And it will come from either spatial heterogeneity, aggregation, or zoning. What I mean by this is if the way I observe the data does not reflect the way that the process actually occurs in reality, I may be measuring something that is not correct. I may be measuring something that is wrong. Think about, for example, if you have these two variables, these two variables, sorry, y and an x. And all the points are observations that we have for y and x. So this shows how y and x are related to each other, right? And what we have here is that if we just check the data as a whole, what we'll see is that y has a negative correlation to x. Okay, so the greater the x, the smaller the y tends to be. If we are able to disaggregate this data and create, for example, two different groups, which we will call two different spatial regimes, if we're thinking about space, but two different regimes, we may find that actually the relationship that we have between y and x is positive and not negative. It's the same points. I mean, we have exactly the same data here. But for the graph that we have in the right, the colored graph, we are able to disaggregate this data into two subgroups. And then we are able to identify a relationship, a positive relationship between x and y. It's just that the level at which this relationship occurs is different. But for the graph on the left, the black and white, I mean, we had just aggregated data, and the data was probably the way the process occurred was different than what we were actually able to observe. So when we're dealing with the aggregated data, we miss this more precise relationship, and then we estimate this negative relationship between y and x. Does it mean that this is wrong? That saying that y and x has a negative relationship is a wrong conclusion? It does not mean that. These variables are indeed negatively correlated to each other, but only at this scale. If we go into a more disaggregated scale, they become positively correlated to each other. So scale really matters for us to see how some variables act with each other. And this example is very nice for this. It comes from Izard's book, and it's the same index. It's a population concentration index. And so Izard was measuring here just how the population was concentrated in the United States. And the idea is that the same index was calculated from the year 1900 and then 1950. So you have this 50 period of data. And what this graph shows is that depending on the spatial scale that you're looking at the data, your conclusion may differ. So if you're looking at this at the county level, and someone asks you, so did the concentration of the population in the United States, did it increase or did it decrease in this 50-year period? Your answer would be, oh, it increased. The population became more concentrated in the United States in this period. And that would be a right answer to it at the county level. At the county level, you had an increase in population concentration. But if you were to answer the same question, but at the geographic division level or at the state level, you would say it decreased over time. So the population became less concentrated over time. So the answer would be different. Again, does it mean that any of the, or you might even say that it was the same, right? That it didn't change. It remained pretty much the same if you are looking at economic subregions. So would any of these answers be wrong? No. They would all be right. You could say the population was more concentrated, less concentrated, or it remained the same. It all depends on the scale that you're looking at. So you have to make sure that the way you're analyzing the data is related to the scale that you are observing the data, so you get the message correctly. Okay, so as I said, if we're looking at spatial data, we must keep in mind Tobles' law, the first law of geography, that everything then is related to everything else, but near things are more related than distant things. So with that in mind, we'll always try to think about the spatial data as something that may show, or usually will show, some correlation. And spatial unities that are closer to each other tend to be more correlated than those that are farther away. So we need to keep that in mind whenever we're dealing with this spatial data, so we can handle the unmet assumptions from the ordinary least square model, so from the classic non-spatial regression. The first one, as I said, being the assumption that the variance is constant, so it's usually not. We will usually be able to perceive some heteroscedasticity in our data. So we have to be able to deal with that. And there are many tools that will support us or help us to deal with it. If the error term shows some correlation, there are two main sources for this. And depending on what is causing this correlation, will have different treatments for the issue. So it may be that your error was correlated because you had some spatially correlated errors. So something that you could not observe in your data after you were able to explain everything that you could about the Y with your X. And you still, there was some heterogeneity, spatial heterogeneity in your data that you couldn't deal with. So there's some correlation in the errors. That's an easy fix, or the problem is not that bad. Maybe I should say that. Because your coefficients will still be consistent. But anyway, if you want efficient estimations, this is something that needs fixing. Or the source for this autocorrelation may be that you have some lagged variable that has been omitted from your model. So you may have some more deep spatial dependence going on in your model that needs to be explicitly handled in the model equation. So you take care of that that source of error autocorrelation that may result in omitted variable bias for your model. So this is a more serious issue that we need to take into account. So these are the things that we deal with when we are talking about spatial models. We have to take care of either a loss of efficiency if we, depending on the assumptions that are not being met, or with bias and inconsistency in the estimations if we do not take into account this spatial relationship. Okay, so how do we do with this? I mean, how do we deal with this? All I'm saying is that, okay, space matters, and unities that are closer to each other, they may show more correlation, so it may be more important to deal with them, and how actually, so we measure these things. To be able to take into account all these spatial aspect of our data, we'll use spatial weights matrices, and this will be our main tool to handle these things. So whenever we talk about spatial matrix, what we have is that we'll try to represent neighborhood as a matrix, in the sense that we'll show which spatial units are closer or relate, or may relate to each other, or may be linked to each other. And if we're doing this, it's a major identification issue, right? If we have, let's say, 500 observations, and we want to represent in a matrix 500 links between these units, we will have a matrix that has 500 lines and 500 rows and 500 columns, right? So, I mean, to identify all that, it may become a very a big problem. The order of this will always be of n squared. So the sample size increases, it's more and more things that we need to identify. So we'll place a more rigid structure to this. So think about Illinois, and the way you will try to represent Illinois first will be as a graph, in the sense that we'll just try to say which spatial unities are linked to each other. And then we can just disappear with the geography or the map itself and keep only the graph, and already think about it as a simplification, a way to be able to handle what the information that we need. So to decrease the number of elements that we have, we'll first have to define some zeros and say, okay, these links, or they are so weak, or these unities are so distant from each other, that let's just say it's zero. Let's just say there is no link at all. So it will make our lives easier in the sense that we will have less elements to deal with. Or again, restrict the number of neighbors for each unit to be able to have a more sparse representation as well. And another simplification is that whenever we're estimating a model, we'll look for a single relationship factor for all the interactions. This is pretty much the idea of a regression, right? We'll just do a beta for all the x's and the y's that we have. So it's just estimating one coefficient. So we'll usually look for a single autocorrelation parameter as well to simplify that. I'll give you an illustration of that. Think, for example, this is where I come from. So Belo Horizonte in the metropolitan region in Minas Gerais, but let's just focus on the yellow area. So think about this space. You have only 6 municipalities, right? How do we represent this as a matrix? So how do we represent this mathematically? The thing is, if you think about Belo Horizonte and what are Belo Horizonte's neighbors, of course, we have, if Belo Horizonte is a node there, node 1, we have the other 2 municipalities that will be considered neighbors according to contiguity, right? If we just see if they share a border among each other. So these would be Belo Horizonte's neighbors. And then we do that to finish our graph. So we will be able to represent the geography following all the neighbors for each of the spatial units. And then we can throw away the map itself with all its complexity and stay with the simplified graph. And from this, we can evolve to a single matrix. And the way we can read this is that, think about the graph that we have here. So the first row in this matrix will be node number 1, right? So it is Belo Horizonte, we know about it, but even if we did not, we have this graph that came from a real geography, and we're trying to turn it into a matrix. So if we check the graph, node number 1 is linked to nodes number 2 and 3. So this is what we have in our matrix as well, right? So row number 1, we have 0 for the first column because that spatial unit is not neighbor of itself. Then we have 1 for column number 2. We have 1 for column number 3, meaning that these unities are considered to be linked or neighbors of the first unit of unity number 1. And then we have 3 zeros saying that that's it, right? The other unities are not neighbors to the first one. And then we repeat that for all the unities that we have, right? So for example, unity number 2, so node number 2 in our graph is neighbor of node number 1. It's not neighbor of itself, is linked or is neighbor to unity number 3, number 4, number 5, and again, not neighbor of unity number 6. Okay, so we have to do that to be able to represent the geography that we had as a single matrix that will link and show all of this. So this matrix will be n by n, a positive matrix with elements W, I, J. The non-zero elements will indicate neighborhoods. The 0 elements indicate non-neighbors, and by definition, a unity cannot be neighbor of itself. We can create this spatial matrix based on contiguity, as I just have shown you, or we can do different aspects as well. I mean, we can create it based on distance and say that a unity will be neighbor of each other if they are within, let's say, 100 miles from each other, or they'll be neighbors of each other if I just take the 4 unities that are nearest to the one that I'm taking into account. I mean, there are many ways we can deal with these matrices and create them based on contiguity, distance, interaction, socioeconomic weights, networks, and I mean, there you go. The last ones, we may face some endogeneity issues, which of course we're not going to talk about today, but still they show some different possibilities for us to be able to create, to represent this neighborhood, to represent these links, the possibility of having some spatial interactions as matrices and incorporate them to our models. So how do we choose? Like what matrix should we use? How should we represent neighborhood? Of course, it really depends on what you're doing. As I said, even the scale of the data must be linked to the scale, the spatial scale of the process that we are studying. The matrix, the spatial matrix, even more so, right? It has to represent what we are dealing with. If you're dealing with pollution, it has to, for example, let's say water pollution. Does it make, if it's a river, does it make sense that I consider neighbors like all the unities within 100 miles distance? Maybe not, because the river flows only on one direction. So these links, the way that we're going to represent neighborhoods, it really must match the spatial process that we will take into consideration. So there's no one size fits all. I mean, there's not a single matrix that will be able to represent all the processes that we have out there. Of course, these matrices must take into account that everything is related to everything else, but near things are more related than distant things. And then, as I said, I mean, the weights matrix must have a direct relation to the theoretical conceptualization of the structure of the dependence. So it must be linked, it must represent the process that we are studying, rather than just reflecting an ad hoc description of spatial patterns. So it's a quote from Luke Anselin's 1988 book that's still like very valid today, that sometimes I wish we could have signs with this to show to people doing spatial analysis, like, please take care that you're not trying to do one size fits all. Like the spatial process must be represented in what you're considering as a spatial matrix and what will represent the space in your analysis. Okay, so can we jump to chapters, to Dani's chapter on spatial regression in the book? Yep.
Any questions? The online room or the in-person room? Maybe you could repeat that, Pedro, because I have my mic off.
So if you have any question from Zoom as well, I mean, this is a good time to ask. Otherwise, we'll just
screen on the side later.
Yep. I mean, the slides are done anyway, so yeah. Okay, so I think we're fine to go. Danny, do you want to? Oh, yes, please, Isaac.
I don't know if this is out of the scope of the lecture, but do you know of any good like libraries or something for making like custom weights matrix? Like if you did want to model like something going downstream, is that, or do you just do that like by hand somehow?
I mean, the easiest place to run weight to create weights matrix. Okay, sorry. So let me repeat the question. So Isaac asked if there is any good place where you can like a tool to create, to make it easier to create customized weights matrices, right? So for example, you can have this river flow weights matrix and how you can create that, right? So what I was going to say is that the easiest place to create weights matrices is GeoDa. Like by far, it's the easiest software, but I don't think it can handle these more customized, yeah. So like the river flow or the wind or anything like that, or if you have like a mountain or something like that. What you can do is you could create your matrix in GeoDa and then rework it by hand, but that's a bit dangerous because the way GeoDa stores weights matrices is very simple. It's a text file. So you can just open it like whatever in a notepad and change whatever you want. So if you want just to keep the counties that are on the direction of the flow of the river, you can do that. So I mean, it's very simple, but it's dangerous to do that by hand. And of course, you can do it for very large areas. And if the other way to do it, which is not as simple, would be using PySal. Using PySal, you can do that. I mean, you can actually have an object that will show exactly like, okay, what are the unities that I have in this direction, and then you can merge these or actually get the intersection between this and the weights matrix, and then crop the weights matrix to make sure that it will do exactly what you want it to do. So PySal would be maybe the best place to do it, but definitely not the easiest. While GeoDa, if it's a simple thing and you don't want to fiddle that much with the weights matrix, would be the easiest way. Just create it there and then by hand edit the weights and get it as you want. Yeah. And the good thing about GeoDa is that you can check your weights afterwards. I mean, you can just pass the cursor over the map and it will highlight who are the neighbors of each of the unities. So that makes it pretty easy for you to say, did I get it right? If you end up editing it. So it's a good tool for that.
He has a general question. Are there packages in R that might help with creating these weights?
Yeah, there are, but so, I mean, Igor has already replied, right? SPDEP and Spatial Reg. I think Spatial Reg does not have many tools to deal with weights, Igor. It would be more SPDEP, but I don't know, do you know, Danny, if they have these, you know, weights clipping tools and merging? I'm not aware of tools like this in SPDEP, Courtney or Igor. I know, of course, you can. Yeah. I mean, you can create the weights matrix perfectly, but I'm not sure it offers that many room like for you to edit it or to play with it. Sorry, as Danny said, replied here, you probably didn't hear. I mean, we have business conflicts there, so we don't really know much about it. Sorry.
Not a problem. Thank you.
Thank you so much. Anything else? Yeah, please, Gabe.
Would it be possible for you to like describe how that process like works at different scales and needs the relationship change in different ways? Like for the slide you have?
Yes, if I had my computer here, it would be easier because I have a slide exactly showing that, but I'll try to give you some, you know, maybe you can imagine the things as well. If I move, let me see if I have at least a point-based thing. No. What we have, the usual example for ecological fallacy is when you deal with, for example, crime data, right? So if you see at the county level, you'll be able to see that usually there is a correlation between a crime and education. So when you have like places that are less educated, usually show more crime, like a higher crime rate. So whenever you estimate a model like that, where you get the correlation between crime and education, and you see that they are negatively correlated, and it was estimated on this aggregated level, you cannot infer anything about the individual, right? You cannot say, okay, so this means that less educated people tend to commit more crimes, because I noticed that there is this negative correlation between crime and education. So this is one of the main or the classic examples of ecological fallacy, when you have an estimation that is for a given scale or an aggregated data, and you want to draw its conclusion to the individual. For space, it would be pretty much the same thing. If you have a given zoning, for example, think about census tracts, and then you draw some conclusions in your model of the correlation between two variables, right? So you say again that you notice that at the county level, crime and education are negatively correlated. If you try to infer that the same result applies to a different spatial scale, and it does not need to be just aggregation level, as I said, it could be just a different zoning. Let's say you're dealing with some I don't know, business areas that are similar to counties in the sense of how much area you have in each unit, but it's a different zoning. So the boundaries will be different. You cannot draw the same conclusion that you got from one model to the other, because it may not hold. So if you think again about Izard's graph, that would be the idea that if you draw a conclusion at one level, that does not mean that that conclusion can be applied to a different level. And if you think about less than aggregation, but more about zoning, if you think about, for example, disease, do you have like a mind image of John Snow's cholera map? So think about the points where you were able to find people dying from cholera. And if you start creating zones there, depending on the way you draw the boundaries of the zones, it may be that you'll get everybody that had the disease more concentrated in a zone, and the others would be cleaner, and the brewery might be divided in half in these zones or something like that. And if you draw, then you may analyze, okay, how related is this to the water source and the cholera deaths? And if you draw the boundaries differently, instead of getting these concentrated spots, you may just get everything in average, right? You may have half and half, like clean, and half infected people in these areas. And then the water source would probably not give you that much information about it anymore, because you wouldn't have variation in your data, right? You would have all these spatial unities with pretty much the same level. Did you get to imagine that? So this would be a problem, a modifiable area unit problem coming from zoning, different zoning, that depending on the heterogeneity that you have in the area, you may draw different conclusions just by changing the way the boundaries are set in a map. Did I answer you, Gabe? Did it make sense? So you may have this map from these two different sources, the aggregation or zoning. They will be the main sources of this, the problem from estimating this. Okay, anything else? Nope. Shall we continue? Danny, do you want to take over? Because now it's the book's notebook. Do you want to launch the binder, please? And yeah, so we can go ahead. Okay, so now what we'll do is we'll shift to the books chapter and start some hands-on exercises from there.
Yeah. Okay, so let's stop sharing for a second to come back to okay, so
maybe post the link on the chat for the Zoom people,
yeah,
to make it easier.
Yeah. Okay. So can folks see online and offline? Cool.
I can see.
Super. And let me just gonna pop the path here, and we will. I think this will let us monitor questions and comments live a bit more easily. Okay, so whoops. A very quick note on what you're seeing now. So this is the website for our upcoming book, Geographic Data Science with Python. This is Serge Ray, Levi Wolf, and myself. It's been in the making. It depends how far back you want to go. You could say 10 years. In reality, more like 5 years. It was going to be out last year, but then a couple of things got in the way of the world of normal life. And hopefully this will be the year that you will be able to see the paper copy, the 3 version of the book. But it doesn't really matter because everything, all the content has been and will be online available for free. So if you're interested, geographicdata.science/book. And all the content is there. The book is very much a mix of concepts and explanations with code weaved through those explanations. And the idea is very much of using code as a medium for communicating ideas and concepts more than, is not meant to be a source of documentation. Now, having said that, there is a lot of code. So if you're interested in learning to program in Python, this is one way. It's a door into that world. So I'm not going to say much more, and I'm going to leave Pedro take over. I will only say about the book that the idea, we've tried to stay true to the title in that Geographic Data Science. So we think of at least 2 personas that would benefit from this book. One is geographic people, or as the Americans seem to use in slang, spatial people. Who like to learn a bit more data science. This is a way of, if you know some geo, you can kind of dress up that with a data science spin, and it'll also give you a window into a lot of the sort of lingua franca for data science these days, which is Python. So the way we've tried to cover the spatial and geographic concepts here is from the data science perspective. And then coming from the other way, from the other point of view, if you're more familiar with data science, if you've been working with data for a while, but not necessarily with the spatial component, but you either realize or start working more with data that does have a spatial dimension that, like Pedro was saying before, has a few, has an allocation, or you can pinpoint it in a map, then this is an introduction of how to think spatially, or how to think geographically about your data, but also, and more importantly, hopefully, if we've done our job correctly, how to think geographically about your problems and how to provide geographical solutions, or solutions that make the most of the spatial aspect of your data. So a couple of very quick housekeeping bits for how we're going to run the rest of the workshop. I don't have PowerPoint, and Pedro is done with his PowerPoint. We're going to have a hands-on version of, or hands-on kind of walkthrough of some bits of 2 chapters. The one, chapter 11 on spatial regression, and then chapter 12 on something that we call spatial feature engineering. And this is the part that I will take over later. So if you want to just sit back and relax and follow along, that's absolutely fine. It'll feel very similar to how it's felt until now. It'll be more like a lecture style. But if you are up for a bit of a challenge and get your hands dirty with some code, you can also follow along on your own laptop, as long as you have a browser and a connection, and you should have a connection if you're beaming into from the interwebs. So the way to do it is I'm going to demo it now, and then I'll leave Pedro. So if you hover over, we're on chapter 11, you can hover over the rocket and then get onto the binder label, and I'm going to press Control just so it opens in a different tab. This is going to spin up something called a binder instance, which binder it's an awesome project. It's one of the best things that have happened to the world of open data science in the last 10 years. It's a service that provides computational backend in the cloud for free for scientific computing. So what this is doing while I'm speaking, those disks sort of spinning are finding a server in the cloud and then provisioning it with a book. And it's going to hopefully, it worked fine this morning, but you never know with these things. It's going to hopefully spin up a Jupyter Lab instance for you to play around with the book, with everything batteries charged, ready for the analysis. So no installation, no conflicts. It's all ready and is ready to go and up and running. And if you want to install it, you probably will spend most of the workshop installing it, but you can also, of course, run the same instance that is running on the cloud. You can run it locally. So I'm going to leave this and pass it on to Pedro. And if anyone, particularly here, is spinning up a Binder instance that has any issues, I'm going to be free floating around the room and we'll be happy to help. One final caveat with Binder. So the economist in me always thinks there's no such thing as free lunch, and the no free lunch here with Binder is that it's what I call an ephemeral instance. So it launches, it's launching now. It launches, it lets you use everything and anything as you would on a local installation of Python. But, and this is a big but for some applications, not for this one, the moment you close the tab, it's all gone and it's up in the ether. So, which is to say, if you make any changes to the files that you would like to keep later, you can, let's say, you open a new tab. Then you come and save these. These will save it, but it'll save it on the cloud. So as soon as you close the tab, it would be gone. So if you're interested in saving that, come here to the file, right click, download, and you can download the file with your changes. And then another bit of another caveat of Binder is that for the same reason that it's free, you can, it'll time out if you don't touch it for, I think it's 5 or 10 minutes. So if you're listening along and you kind of forget that it's on, you might get disconnected and you just have to respin it up again and you'll get a new instance. So again, you lose your changes, but you can still use it again and carry on following interactively. Okay. So if there's any questions, drop them on the chat or just raise your hand if you're in the room, and I'm gonna let Pedro take over here.
Okay, thank you, Danny. So have you all been able to launch this, to start this notebook? Do you need a few more minutes for us to wait for you?
I would say get going, and if people have issues, we can cover them. I was going to say, maybe you can ping yourself to see how you're covered on the camera. Let me see how that would work. There you go. Great, thanks.
Okay, so again, if you have any issues, just let us know and we can wait. So what, as Danny was saying, this is a very interesting feature of the book that we are able to follow follow through the book within this notebook environment, which means that we can actually get the code running as we see it. So from where we stopped from the slides, I mean, what we got to do now is actually to be able to load some data. So let's start some data set and we'll load all the information. As I mentioned before, we're going to use Airbnb point data. And with that information, we're going to create, to run some non-spatial regressions first, see how we can deal with spatial dependence.
Yeah, carry on.
Yeah, or no, I'll wait.
Just
Got it?
yeah, I think that now
Okay.
easier.
So we'll run non-spatial regressions just so we can see like what this data looks like and the heterogeneity or the spatial heterogeneity that we have in the data, and we'll go through a few ways of getting that taken into account in our models. Okay, so if we just skip the text, and of course it would be great if you could review these later. Let's just skip it to the second cell that we have in this notebook in the book. So again, if you're not being able to follow along, just let us know. But this cell, what it's doing is it's just importing all the libraries with the tools that we'll need for this application. So what we have here is that it's importing PySal, PySal-lib, and PySal for the weights, and PySal Explore for the exploratory spatial data analysis. It's importing NumPy, Pandas, and GeoPandas, so we can handle the data and do all the data wrangling that we need to. It's importing Matplotlib for the maps, Seaborn for nice-looking graphs, and contextually to do some base maps in the maps that we're going to run. So if you select this cell, you can just do Control Enter or Command Enter, depending on what you have. Yep. And you see the star sign here shows that it's actually running. And then you get a few warnings because you didn't run the first cell, which was muting the warnings. But anyway, no worries. Yeah. So, and then the star sign is gone, right? And you have a number 1 here showing that it was run successfully. Or it was run, right? And then, of course, you didn't get any important error message below, so everything went okay. Good, so let's load the data. So for the data for this exercise, we're going to use this regression db.geojson, and we're using GeoPandas to read this file and storing it in this db object. So I'll run this cell again. And the variables that we have here for this data is each of the observations show 1 Airbnb unit. So what we have for information is the number of people that it accommodates, the number of bathrooms, the number of bedrooms, number of beds. I mean, I won't be reading this for you, and because of course you can read it much better than I can say in English aloud. So anyway, I'll just run this cell again so we can store this list with the name of the variables. And then what the book does here, this section of the book will do a more, it's still a very quick, a very short review of non-spatial models, but we've been through these already in the PowerPoint presentation, so I'll just skip it again. A final import here, which is the main library for spatial regression in PySal. So it's importing from PySal model SPReg. So this is the library that is mostly maintained by here, the Center for Spatial Data Science, so under Luke Anselin's supervision. So let's load this library as well. So at this point, we have been just loading things, right? Data, loading libraries to make sure we have everything correct. And with all that in hand, I mean, we can finally estimate a non-spatial regression using PySal. So what we'll use here is OLS from the SPReg module in PySal. The way this command is structured is that we have to send at least, the most important here are 2 arguments, the first 2. So the first one is what's our dependent variable. So in this case, what we're doing here, if you're not very familiar with pandas, what we are doing here is that from within this object DB, where we loaded our data into, we are choosing the column that is named log price. So that's the column we are selecting, or we're slicing from this DB, this database object, and we are converting it from a slice of a data frame. We are converting it only values. So we just want the values that we have for each of the observations. So this is what we're saying by using this. So we are calling the command spreg.ols, so the method to estimate the ordinary least squares within OLS. We have the values for the prices of the Airbnb unities as our y variable, as our dependent variable. So we're just sending this information to the method. And here we're doing exactly the same thing, sending the observation on the x variables to the method as well. This is what really matters, where what we really need to do for the method. But here we have things to make it look better, to make we can understand easily what we get as results. So we're just informing the method that the variable y, its name is log price, And for the variables X, their names are stored in this list that we have created 2 cells behind. Okay, any question about this? No, all fine with the structure of the command? Good. Let me run it. And okay, done. So we have fit this OLS regression. And now, of course, we can see the results. So I'll select the cell, which is marked as 7 here. For me, it's going to be 6, right? And then the zoom is an issue. Danny, can I fix the zoom here?
Okay, you what?
Get zoom out a bit.
You can type there.
Here?
Yeah.
Okay, good. Okay, so these are the results, right? So from here, we have all the variables that we had selected in the first cells as X variables, so the ones that are explaining our log prices. We have all the coefficients, which I'm not going to interpret, but if you have any regression background, of course, this is just easy for you. And the p-values to show us the significance of these coefficients. And here, before we get right above the coefficients, we have a summary information on the model. So we know the R-squared, we have adjusted R-squared. We can tell what is the log likelihood of this model. We have a Kaika and Schwartz criterion to compare models if we want. I mean, we have all the usual summary information on models coming from SPReg. What we have below the coefficient table is some regression diagnostics. So we can see a multicollinearity condition number to be able to assess how collinear our explanatory variables are. We have tests on the normality of errors, and we have some diagnostics for heteroskedasticity. Okay, so all the standard results from a non-spatial regression, SPReg will give it to you, so it will allow you to interpret these results accordingly. Okay, so this is non-spatial regression, right? I mean, of course, you can do 2-stage least squares. You can do like many other combinations of non-spatial regressions. You can do pro-bit estimations or non-spatial pro-bit. There are many models that SPReg in PySal will offer you, but we're here to deal with spatial regression, or how to charge up your regression, adding spatial content to it. So let's just move a bit ahead and let's talk more about space. So one thing we can think about space is that sometimes what we have is that space shows, as we had on that graph that I've shown you, the black and white and the one that had colored dots in it, is that the space may be a feature in your data that will show that you have a different relationship between your variables according to the area or the spatial tag that you have on your information. So what I'm trying to say here is you may have spatial heterogeneity in your data, meaning that the relationship that you are actually studying may change depending on where the data is coming from. A way to see that is if you have information on what would be the source of this heterogeneity. So here we have the Airbnb information. Of course, I mean, we can expect some differences between Airbnb locations if they are coastal locations and if they are not coastal locations. So these may be a known source of heterogeneity. And if that's the case, we can just bring that information to the model and see if that's actually the case. So space here is being added to the model as something you can easily observe, like is that Airbnb located in the coast or is it not located in the coast? So you know, you can observe the spatial feature, you know that it may be a source for heterogeneity, so it's easy for you to model that. So what this cell here is doing is creating a Boolean variable, so a binary variable, true or false, to identify the locations, the Airbnb locations, as coastal or non-coastal locations, okay? So here's the thing. What we have here is that first, we're creating this object is coastal, and it's just being created from the information that we have on the database, saying that whether the Airbnb location, the Airbnb point is located in the coast or not. And then we can get the residuals from our model that we've have just the non-spatial model that we've just run. We can get the residuals, that U vector, and split it between unities that are in the coast and unities that are not in the coast. And then we can create a histogram. We can create a histogram out of this information to see if there is heterogeneity coming from that, right? To see if coast is indeed a source of spatial heterogeneity in our data. So this plt.hist, so plot.hist command will create this histogram for us. And then you have like the line 0, legend, all these other information being added to the graph. And if you run this, and I'll do it now, of course, the result was there already, but you have this, the residuals being plotted, the distribution of the residuals being plotted for you, comparing what you get when you from Airbnb locations in the coast and Airbnb locations that are not in the coast. Of course, you would expect the average of the residuals to be 0, right, for the whole regression. And what we see here is that it is more true for coastal unities than it is for non-coastal units. But still, the distribution is not that, they are not that different from each other, right? So what we can see from this exercise is that although being on the coast may be a source of heterogeneity, it is not that, like, it's not that important, or it's not that different, right? So it's not that much of a source of this. So anyway, we can still work with this to actually test what we have here. So we can check whether these distributions are indeed different or not with the within all the commands that the book that is showing here. Let me just skip this part, because what we're doing here is just plotting the residuals that we have according to location, but let's skip it so we can go to more important bits. And just go ahead of all this, because it's just plotting the residuals. And this is it. And we may actually, now what we may do is to assess this spatially, not only in terms of being the coast or not, but seeing throughout the map, how can we assess the residuals that we have from this model. So let's run this cell 13. I don't think it will work because it's just reweight. So wait, let me go back a bit where the weights are being created here. So let's run this cell 12. So here we have the spatial, no, we have, sorry, 11, this cell here. So here we have the spatial weights being created. See, KNN equals weights.KNN dot from data frame. So we are creating a KNN weights matrix from our data frame. So I'll run this. And now I'll go to the one that I actually wanted to run. And what we'll do here is the following. We will create this KNN matrix based on the nearest 20 neighbors. So our weights matrix will show, like, the links will be for each of the spatial unit. It will get the 20 other spatial unities that are nearest to it. So it's a type of a distance weights matrix. It will then row standardize it as the standard for spatial regressions. And then we'll be able to assess these points in the map to see how they are distributed across it. So I'll run this whole cell. And the star sign is still there. And what it will show us is clusters of these residuals, showing to us whether we are able to identify spatially if low values of residuals or negative value of residuals tend to cluster close to each other, and if high values of residuals also tend to cluster close to each other. Can I increase the size of this figure, Danny?
You can rerun it.
Yeah.
The top on the cell. Yeah. Oh no, sorry. Where?
I just want to zoom in, but yes, if it weren't okay. Oh, here we go. This is okay. I mean, I think this is enough. So what we can see here is that we do have some locations in the map that tend to concentrate higher values of the residuals, and some locations in the map tend to concentrate lower values of the residuals. So we tend to have some spatial clustering of these residuals. And of course, we shouldn't observe these, right? If the assumptions, the hypothesis of the non-spatial method of the ordinary least squares, if they were met, this shouldn't exist. We shouldn't have these correlated residuals like we're seeing here. So it shows us that, I mean, at least indicates to us that we may have an issue with our data. Of course, we have a big suite of formal tests for this, which we are not going to see today, but they are all within SPREG, they're all within PySal. So, I mean, we can formally assess this to see if our residuals are indeed spatially correlated. But just by plotting them on a map like this, it's already some information to show us that there is some spatial correlation going on. So we need to deal with space within our regression framework. So how do we bring it? How do we bring space into this regression framework? Again, let's skip a bit some parts of the chapter because I don't want to run out of time, and we are almost running out. So let's skip these spatial fixed effects, and let's go straight to spatial regimes. I'll click here again, because then you can see the structure of the book. And then there it is, spatial regimes. And let me close this again. Okay, so what we can do here is to try to replicate the graph that I had in my PowerPoint presentation, in the sense that we can just try to run, or we can run a different curve or a different line, a different regression for parts of our data, right? So we can group our data, and here we're grouping it by being the coast or not. So we can use that information and run the coefficients differently for each chunk of the sample, like for each group that we have in this sample, the observations that are in the coast, the observations that are not in the coast. And then we will be able to assess whether the coefficients that we have in our model, they are stable across the observations, in the sense that they are roughly the same for observations that are in the coast and for observations that are not in the coast. So we'll be able to assess how different these coefficients are from each other, meaning that the relationship between the axis and the y is different depending on where that observation is located. Okay, so again, if you're not being able to follow, just let me know. But let me explain to you what we're doing here in this cell. So here we're estimating the same model that we had before, spreg.ols, but we are adding these regimes to it. So what we're doing here is that we will estimate different beta coefficients for the different types of observations, right? According to whether they are in the coast or not. So the structure of the command of the function is pretty much the same as before. First, we submit our dependent variable. So here we are taking a slice of the column log price from the database, converting into values. Then we do the same thing for the explanatory variables. And then what is different from before is that as a third argument in this function, we submit the labels that will show us, or that will tell the method if that observation was in the coast or not, right? So it's the 0, 1 observation variable that highlights which of them are in the coast, which are not. And then everything else is just optional. So, I mean, you don't need to worry about this, but what this is saying is that we're going to have a different constant for each of the regimes. So each of the groups, each one of the groups of observations will have a different constant, and that the error term is also going to be separate for each of the groups. So these are all default arguments that we have in the method. If you just, for example, if you want to try it there, you can just delete these and you'll get the same results because these are default. And these, as I said before, it's just so we have more information in the resulting table, the results table afterwards. Okay, let me run this. You did run that fast? Yeah, pretty fast. And as a result, I think, Danny, here I'll make it different. If you allow me, I'll diverge from what we have in the book, just to show it how just to show you all how SPReg actually reports this, but then we may see what we have. So I'll just do print M5, which is a model.summary. I need to type it right, otherwise, of course, it won't work. Okay, so you can do the same. Oh, if you don't know how to create a cell below, what you have to do is to select the cell. You see, it has to be selected, but not in this edition mode. So you can click on the cell and maybe, and then just click on ask it to get it selected, but not in edit. And then you just type B and you'll get below a cell, right? So it will create a cell below for you. Okay, and then type in print m5.summary, and this is the default way that SPReg shows the results. So first we have here all the information on for regime 0, or the observations that are not in the coast. And then we have for regimes number 1, which mean the observations that are in the coast, right? So we have different betas for these groups of observations. Then we have the standard again, diagnostics. And what I wanted to show is this, the child test, so the regimes diagnostics. And what this is checking is, this is checking whether the coefficient for accommodates or for bathrooms or for bedrooms, it's assessing whether it is statistically different across equations. So if it's across regimes, if it's statistically different for the unities that are in the coast and the unities that are not in the coast. Okay, so what it's testing, actually I'm saying if it's different, but the hypothesis, the null hypothesis here is that the coefficients are the same. So for example, what we have here is that, highlight it, yeah. What the child test is showing us here is that the coefficient for bathrooms is not, I mean, you reject the null hypothesis that the coefficient is equal for each of the regimes. So what we know is that, what we can infer from this is that how the number of bathrooms affect the price of the Airbnb location changes whether that Airbnb location is in the coast or it's not in the coast. Okay, so the number of bathrooms, the relationship between bathrooms and the price is different for Airbnb locations in the coast and Airbnb locations that are not in the coast. And the same thing is valid, for example, for this rate private room. See, here we do not reject the null hypothesis. So what we have here is that the coefficient for this variable, so how private room affects the price of the Airbnb location, does not change whether that observation is in the coast or not in the coast. I mean, if you want to, we can just go back to the regression and you can see this. So for example, private room, the coefficient for regime number 1 is minus 0.55, and for regime 0 is minus 0.52 or 53. So of course, they're not statistically different from each other. And for bathrooms, it was when the unit is not in the coast, the coefficient is 0.14. And when it is in the coast, it's 0.25-ish, right? So, I mean, it is statistically different. They are statistically different from each other. Okay, so here we're able to bring space into the regression without actually using a lot of spatial tools. We're just disaggregating our sample according to its spatial location. So we have a different set of coefficients for locations that are in the coast and they are not in the coast, and taking into account so how space shapes or how space mediates the relationship between the explanatory variables and our dependent variables. And in that sense, we are able to identify how a relationship is different according to the location of the observation. Got it? Okay, good. So this is it. Let me skip this. This is just the book explaining everything that I have told you already. And now let's do a more explicit account of space in the sense of spatial dependence in our model. So again, let's go straight to some coding. The first model that is being shown here is what is called the SLX model. So it's where the spatial aspect or the spatial feature of the model is in the explanatory variables only. So you take your axis and you think about, okay, so the prices of the Airbnb, they depend on its characteristics. Good, but do the prices also depend on the nearby Airbnb locations, the characteristics of the nearby Airbnb locations? So if I have an Airbnb location that has many rooms, the relationship between number of rooms and price, does it depend or does it vary whether the nearby Airbnb locations also have many rooms or not? Maybe if they have, I have a large Airbnb in an area that has only small Airbnbs, maybe that will change how the price of that Airbnb location, right? So maybe the context where that location is or the attributes of the competing locations, maybe they will affect the price of a given Airbnb location. So this is what we will be able to measure with this model, how the characteristics of the competing Airbnb locations or the locations that are in the same area, how they affect or they do not affect the price of a given Airbnb location. So what do we have here in this comment? First thing is, what we have here is, what is being done here is that first it's being, the code is selecting only the columns and the database that contain the keyword PG. So it's just selecting these type of variables for this group of variables first. And then it's computing a spatial lag for each of them. So by spatial lag, it's just checking what is the average of the attributes in the neighboring Airbnbs and creating a matrix with that information. Then it just renames the columns to add a W to show that it's taken into account, like just to label the average in the neighborhood for each of the variables. And then it's dropping just this variable, the WPG apartment. So this is what we have in this comment. Yes. Jonas, if you want to open your microphone and make your question, because so you're asking if OLS regimes function create summary variable, am I right? What do you mean by summary variable? Okay, it's not like a variable, right? It's just an attribute of the object, yeah. So what we did was just to print that. It's just where it stores the results in text format. Not sure if I was able to answer it to you, if I got your question right. So, of course, you all couldn't see what Jonas asked was just that, like if the OLS regimes functions was creating a summary variable, and all functions in all methods that we have in SPReg, they will create this summary attribute for the function. And the summary attribute is where the results are stored as text. So that's why we just print it and we get all the table with all that. So you just call summary and as Danny has just replied. Okay, so let's continue here. So what we're doing here in this cell, as I said, is just creating this WX matrix where we have the observations, like the attributes of the Airbnb locations in the neighborhood. Okay, so we're storing here in this matrix the attributes of the neighbors, of the neighboring units, to add it to the model. So here what we do is we get our database, we select the variables that we had for the X, and we add to it the WX that we've just created. Okay, so we just join these two things. And so what we're doing is just adding to the data frame the average of the axis that we have just created for the neighborhood. And then we run this M6, model number 6, using the same command that we did before. So spreg.ols, dependent variable, then independent variables. But here, of course, it's a different name, right? We have just created this SLX-exog. So all the variables are stored here. The axis that we had before, this new spatially lagged axis, so the axis for the neighborhood, name Y, and then again, just creating the name for the axis as well. All right, before running this, I think I'll just stick to the summary one more time. So I'll just do again, the same thing as before. So we use a standard printout. So I'll do print m6.summary. Okay, Janus, did you get the whole idea now of the summary? So as you can see, it works for all comments, not only OLS regimes. Let me know if you still have questions about this. Oops, I forgot to run the one before. Sorry. Done. And now here. Okay, so here it is. What we have here now is our summary of our model. So the axes that we had before, they are all here. And we've added a spatial lag of some of the axes that we've selected to add in the model as well. So now we're taking into account not only how this PG house or PG other or PG condominium, how these attributes of an Airbnb location, how they affect its price, but we are also assessing how the condominium or house or other or these attributes of the neighboring Airbnb locations, how they may affect the price of a given Airbnb location as well. Okay, so we're bringing space into a regression here by considering not only how the attributes of a given observation affect its dependent variable, but also how the attributes of the neighboring units, the neighboring locations affect a given location as well, a given Airbnb location, right? Then you have all the diagnoses again, I mean, everything as standard. Okay, let's move a little bit ahead and let me go to the structure again of the chapter. Here it is. And finally, I'll skip spatial error model because we're running out of time, but spatial error will just, as I told you before, it will just sort of help us to fix an inefficiency in the model that comes from this spatial autocorrelation of the residuals. So it happens, what we're trying to fix here is when we have some unobserved characteristic that makes the residuals spatially dependent or spatially correlated to each other. And then we just want to get that fixed so our coefficients have an efficiently estimated standard deviation. So it's not like the most of the important issues that we can have in a model. So I'll just skip it to spatial lag. And then here's something important, right? Because a spatial lag means that what we have is that the dependent variable in the neighborhood is related, or sorry, the dependent variable in their neighborhood affects the dependent variable of a given locality of interest. So it's a correlation between the Y variable in the neighborhood and the Y variable for each of the localities. And this is very important because if this is significant, if let's say the price in the neighborhood of the Airbnbs in the neighborhood, if it affects the price of any given Airbnb location, and that is not taken into account in the model, we will have omitted variable bias being caused by this. And then, of course, our coefficients will be all biased. And then, I mean, it doesn't make sense to run a regression with that, right? So this is a very important aspect of a regression that we need to take into account. So let's just go straight into the cell here, and I'll explain to you how the command works and what it means, all the lines mean here. So what we're doing is, as model 8, we'll be estimating a spatial lag model. By spatial lag model, we mean exactly what I've just said, that the lagged dependent variable will be part of the explanatory variables in our model. This is something really important because differently from time, I mean, time works just in a single direction, right? The past affects the future, but the future does not, at least should not, as long as we know, right? Maybe it affects and we don't know yet, but the future should not affect the past, right? So you never know if someone has already created a time machine or something like that, that this is happening. But as far as I know, past affects future, future does not affect past. Great, but with space, it's not like that, right? With space, what we have is that, for example, Illinois may affect Indiana or Michigan, and Michigan may affect back Illinois. So we don't have this single directional causality. We may have this multi-directional causality going on. So this brings endogeneity to our models. And if it brings endogeneity, we need a very special set of tools to fix it. So GM lag is exactly that. It's a method that will fix this endogeneity for us. So what we have to do here is to provide a dependent variable, independent variables, so the explanatory variables, the same thing that we did for the OLS. The only thing we will be adding here is the weights matrix, right? So we will let the method know what are the neighboring units. So we can check whether the prices of those units, they are related to the prices of the Airbnb locations, okay? So again, I'll just add a summary to the bottom of this. Print m8.summary and run this cell. Let me get rid of this thing. Nope. Here. Okay. Oh God, it went all the way. Okay, so here are the results. So what we have now is that the log price of the Airbnb unities in the neighborhood are being considered in the model, right? So we can see how related these things are. We can see that this is significant. So we have that this relationship is significant. So it's something important we needed to take into account so we don't have a bias model. And it will change the way we interpret our coefficients, because now what we have is that the number of bathrooms in a given location will affect its price. Great. So if you consider a location with a different number of bathrooms, it will have a different price in average, right? So locations with more bathrooms will be more expensive in average. Great. So can we think maybe if we add a single, like a unit of bathrooms to all the locations that we have, we can estimate how that would affect the total prices in the end. That would be a usual interpretation of this coefficient. But now that we have a spatial lag, the things will not stop there, right? Because if the price of an Airbnb location increases, that location is in the neighborhood of other locations. So by having that price increased, it may affect the price of the neighboring locations. And then you will have these endogeneity going on, like it's like throwing a pebble in a lake, right? You will have a wave of effects that will affect all the unities that you have in your sample in the end. So the way we interpret the coefficients now that we have a spatial lag is that we'll have some direct effects that are the usual interpretation, that have the usual interpretation that we do for coefficients, but we also have some total effects that take into account this pebble throw at a lake effect, right? So the whole endogenous effect that we have going on. So we can use a spatial multiplier to actually be able to calculate what is the direct effect and the total effect that we have from adding this to our model. So of course, the book brings more details into that. Look, Anseli's 1988 book will explain that in many details, so you can see how this is derivated. You can see how to calculate a spatial multiplier, how to get this total effect interpretation for your coefficients. I mean, it's all there. Unfortunately, we do not have time to go into the interpretation of the results here. It was more just to show how to actually estimate these models. So there's like plenty material out there on how to interpret this and what this means conceptually in terms of the process that you are studying or that you'll be evaluating when you do this. All right, any questions or anything like that? I stop here. We've seen already 2 or 3 ways to actually bring space into your regressions, and Daniel will show many more after the break. But if you have any questions on this part, now would be the time before we go for a coffee. No? Okay. Anyone out there? We're all good? Okay, so let's do a 25-minute break. Yes, and we'll be back at 3 p.m. Chicago time. You can do the math, and I'm terrible at it, so I won't even try to do it for any location out there, what time it would be, but just 25 minutes from now. That should be easy enough. O'clock, 25 minutes from now, o'clock, according to our British friend out there. Okie dokie, fellows. See you in 25. Thank you.